Hello, and welcome to today's webinar, Introduction to Geodesy with MATLAB. My name is Dave Forstot, and I'm an application engineer here at MathWorks. Now, when I say Introduction to Geodesy, what do I mean? If you're already a GIS professional or very familiar with Geodesy, you may have a good idea. For the rest of us, what does it mean to specify position in the planet? Now, we've often heard about things like latitude and longitude or altitude and elevation, but today's goal for me really is to have a good understanding for all when we walk out of this session about what it means to define position on the planet. So we'll have a quick introduction to set this problem up, and then cover coordinate systems, and we're actually going to spend most of our time covering coordinate systems, and we'll take a brief tangent to cover heights. That'll be clear in time, and then we'll have a quick look at some projections. But let's set up the problem. Does your GPS lie? Let me explain why I asked that question. So today's session is really about understanding the conventions for defining position. And here I'm using MATLAB to explore some of these ideas. And right now I just want to run, do we have a problem? And we're opening up a map that has 3 markers. Each of these markers is actually located in the University of Southampton, which is a university in the UK, southwest of London. Now, the interesting thing about these 3 different markers is they have the same numeric value for latitude and longitude. But the 3 markers are in very different locations. So if you were delivering a package to this location, maybe it's a pizza delivery, or maybe it's a UAV delivering an AED, a defibrillator, you want to probably make sure it gets to the right building. Now, how do we have 3 different latitudes and longitudes? Well, going back, this is the problem. This is what I want to explore. Hopefully when we walk out of today's webinar, we'll understand how this comes to be. But first, let me say, your GPS does not lie. Nor does it make assumptions or you necessarily make assumptions. But inherent in specifying position, there's a lot of other information. So let's look into coordinate systems. Now, there are many coordinate systems we use commonly. Cartesian coordinates, when you give an x and y location for a position. Good for rectilinear features, but if you're talking about things that maybe are more circular, you might be familiar with a polar plot. And I want to cover polar plot because it does come in to some useful points right now in a very simple 2-dimensional fashion. We often have some angle that's measured as, how far from a particular point of reference. Commonly in a polar plot, it'll be your angle off the x-axis, the positive x-axis. And then you'll have a radius that is how far from the origin you'd be. And so with those 2 coordinates, the angle off that x-axis and the distance from the origin, the radius, you can define any position on a flat circle. Now, spherical coordinates take that same idea and just add one more value. You have, again, that angle from the positive x-axis. We'll call that phi over here. But you also have an angle of declination from the z-axis. So you can be around and down, and then, again, radius out. Now, what system you use really kind of depends on what you're describing. So let's talk about the Earth. This is the first quiz for today. There is no partial credit. What's the best approximation for the shape of the Earth? Is it a flat disk, a perfect sphere, an oblate spheroid, or something else? Now, in general, we're okay with that spheroid, that oblate spheroid, and that's particular to now. I'm pretty sure if we asked this question maybe several hundred years BC, we'd get a different answer. But even as far as 200 years BC, we had a pretty good understanding about the shape of the Earth. Now, before I talk about a spheroid, let's cover some basics on an ellipse. An ellipse is like a circle, except it's been squished in one direction. So we've got this semi-major axis. This is how wide it is in this case. And we have the semi-minor axis, which is how tall it is. Now, if you have these two numbers, you've described an ellipse. You can also describe an ellipse with just one of these and the flattening ratio. That's the ratio between the length or width and height. And whether you talk about a flattening or an inverse flattening, with one of the axes lengths or semi-axis lengths and the flattening ratio, you can also define an ellipse. So let's go back into MATLAB and take a quick look at some of these ideas of the shape of the Earth. So let's start with a unit circle. A unit circle, again, is one where the radius is 1 in every direction. So from our origin, we have a 1. Once we want to make an ellipse, that's now changing depending on whether we're going, let's try that again. There we go. So here's that circle again. If we look at an ellipse with a flattening ratio of 1/2 or an inverse flattening ratio of 2, that flattening ratio of 1/2 means it's half as tall as it is wide. Or in this case, the semi-minor axis is half as long as the semi-major axis. If we look at a flattening ratio of 1/5, it's getting a little bit rounder. Now you can see it's only 1/5 less in length along the semi-minor axis as it is along the semi-major axis. And when we get to 1/50th, you'll notice that's very, very close to that original circle. Now, I stopped at 1/50th because that's easy to see on my screen, even at this reduced resolution. You can see a little bit of gap there. The Earth's flattening ratio is around 1/300th, or the inverse flattening ratio is 300, the inverse of 1/300. So it's not a really big difference when you're looking at something that happens to be of unit dimension. So in this case, my semi-major axis is 1. But when we start talking about the actual planet, these numbers become much larger. So if we look now at spherical coordinates, the mapping toolbox is so in MATLAB we have a toolbox model. The mapping toolbox is what gives you the ability to read and write geospatial data, display geospatial information or other data on a context of a map, and also to deal with things like the geometry. So if we look into the mapping toolbox, actually we can just go right from the documentation for mapping toolbox. In the getting started, we have understanding latitude and longitude and understanding spherical coordinates. These are kind of the entry point you need to understand to be successful using any kind of mapping tool. So looking specifically at understanding spherical coordinates, we cover the idea of the geoid and the ellipse and ellipsoid that we just mentioned. And I've used ellipsoid and ellipse interchangeably. An ellipse is a two-dimensional construct. An ellipsoid is what would be created if you rotated that ellipse around that semi-minor axis. So what this is saying is the Earth's a little bit shorter than it is wide if you think about north or the semi-minor axis being up. Now there's ways you can represent the shape of the Earth in MATLAB. And one of the simplest ways to represent the Earth is with a reference sphere. Now we've already covered that the sphere is not the best representation of the Earth unless you're looking at a very small scale. If you're looking at the entire planet or large areas, a sphere is a good enough approximation most of the time. And if we do that, the radius of that sphere would be about 6,000 kilometers, 6,371, give or take. If we wanted to look at this in miles, because I happen to be in the US and miles are the more conventional distance unit, we can look at that same sphere here, my reference sphere, and change its length unit to miles. And look at that a sphere's radius again, and it's about 4,000 miles in radius. 3,950, we'll call it 9. The interesting thing about a sphere is the radius and the semi-major axes and semi-minor axes are all the same number. And the flattening ratio is going to be 0 because the semi-major and semi-minor axes, the ratio between the two is 1, and 1 minus that is 0. If we want to look at an ellipsoid, the reference ellipsoid is a set of objects to represent some common shapes for ellipsoids we use often. Now, there's some for other planets in our solar system. So those of you interested in position on places other than Earth, these would be useful. Now, we also have many for the Earth itself. And in a moment, we'll look at how and why that happened. But as we define an ellipsoid for Earth, we can see there's a little bit more information than just a radius. As a matter of fact, we can't have just a radius anymore because the semi-major axes and the semi-minor axes are different. And so here you see that inverse flattening ratio that I was talking about before, and the Earth is very close to 300. Now this is for the World Geodetic System of 1984, WGS 84, and we could take one more glance at what some of those distances might be. And if we remember, the circumference of a circle is what, 2 pi times r. This doesn't quite work for an ellipsoid, and we'll cover that later when we cover distances. But to properly measure distances on a sphere, we want to take a few different approaches. So the ellipsoid dimensions we just looked at, and the circumference, and those are again in meters, because that was how we defined this reference ellipsoid. So how do we have so many different representations? So we just looked a little bit at the flattening and then the way to represent a sphere or an ellipsoid and why you use these, because they capture that change in dimension. An ellipsoid is this ideal concept. It has no real manifestation in reality, in the Earth, I'd say, or in any planet. But if you can define this ellipsoid with its 2 parameters and say where you're going to tie it to the planet, that initial point, and the orientation, now you've got something that's realizable, a concrete specification. And there are many, many of these. These are called datums. Now, if you'll accept my very distorted cross-section of the Earth, or a cookie that's been nibbled on, we could find a place to tie a datum over here. Say, define this ellipsoid, initial position right about here, and orientation along this path. And that might be great for this location on this side of my chewed cookie or distorted cross-section of the Earth. And so that would be a great datum for us to use here. But on this other side, it's atrocious. If we wanted to say something that might be a little bit more globally optimal, we could use an entirely different shaped ellipsoid. Tie it in a different location, say perhaps here, or even tie it in that same initial point, and have a similar orientation. But these are 2 very, very different datum, and are going to have different advantages and disadvantages. Now, the reason there's been so many datum is because we've needed to have accurate ways to specify position at different points in the Earth at different points in time. So in Great Britain, there was a datum defined, OSGB 36, and it was based off an ellipsoid definition called the area ellipsoid of 1930. Again, this is my chewed cookie or gross cross-section of the Earth. This is just for illustration purposes. But meanwhile, not too much longer after this datum definition, World War II happened, and the European countries needed to be able to effectively communicate position. And so another datum was created, the European datum of 1950, and it was based off an international ellipsoid of 1924. Now, both of these served a very good purpose at the time, and now, after we've thrown a bunch of artificial satellites into the sky or space, we have a good idea of where the center of mass for the planet is. And perhaps neither one of these have been centered such that their ellipsoid is centered on the center of mass. So we've had many different datum evolve over a time, some that take on a very local purpose, some that take on a more international or global purpose, and now we're refining this even more with our understanding of the absolute geometry of the planet. So before we go any further, I want to take one quick look. I've mentioned latitude and longitude a number of times. And tying back to that, do we have a problem question? Our latitude is a measure, an angular measure of how far off the plane of the equator we are. So where we define that ellipsoid, that would be the angular distance from the semi-major axes. Does that make sense? I hope so. Now, longitude is actually the angular distance around the globe, and it's measured from, in this case, the prime meridian, which happens to go through Greenwich over here. It's right inside of London. So if we go back to that initial visualization, let me bring that back up. What we had was 3 different positions using 3 different datum. Today, if you looked at a GPS or your smartphone, it would likely report to you your position using something like WGS 84, the World Geodetic Survey of 1984. However, I mentioned those 2 other datum, the datum that was defined to specify position in Great Britain, as well as a European datum. Now, when you have datum that have evolved over time but designed for the same region, the differences are going to be very, very small. However, if we use maybe the North American datum, any one of its manifestations, this may have even more error over here because that was designed for North America. These 3 are all pretty close in terms of geography, but in terms of distances, we're going to see in a few moments that given the scale here is 20 meters, these are 100 plus meters apart. Now, one more interesting fact is, until we had these devices that we could hold in our hand that would give us an exact position in latitude and longitude, the way we determined where we were was through a very manual effort of surveying from a reference position. Now, if you defined that datum at some point, fixed point, that's where the absolute truth is, you could survey from one point to the next, to the next, to the next, and eventually you'd have a point that's relatively close to where you're interested in, and you could measure your relationship to that point to come up with your position. As a result, the positions that have been recorded over time against many of these datums have had opportunities for error. Because even if we say these were very, very accurate measurements, error propagation from one to the next, you could result in very, very small errors accumulating so that you had large errors when you get to a place very far from where that datum was defined. And so when you convert from one datum to the next, it's more than just an operation of potentially translating the center of that ellipsoid definition or scaling or rotating. As a matter of fact, the definitive way for converting between the different North American datums is based on a least squares fit between many, many survey points in the different datums. So I mention this because when I was converting a single numeric value of latitude and longitude between the different datums, the value I got for the European datum of 1950, I actually got 2 different values from 2 different calculators, and the other one happened to be in a completely different building. So that was just different implementations of the conversion routines. Now, the point is that latitude and longitude is not sufficient. It's necessary but not sufficient to define our position accurately. So that covered latitude and longitude. I'll buy it briefly. What about height or elevation? So let's say you're flying in a plane and you hear over the speaker that you've reached a cruising altitude of 40,000 feet. I'm assuming now you're probably in a U.S. or flight because we're saying it's in feet. I have no idea what that would be in meters. But when you're flying at 40,000 feet, what are you 40,000 feet from? Is it that ellipsoid definition we were just describing? Some vertical datum, some agreed upon reference, maybe say sea level? The geoid, which actually we'll cover in a few seconds, but it's an equipotential surface. It's a place where, in theory, the same gravitational force is felt across the surface of the planet. Or is it ground level? Now, the reality is you can measure distance from any one of these, and they're very, very different sometimes. Certainly ground level from the ellipsoid definition, and the vertical datum. Perhaps it's unclear, and you should ask again later, my favorite magic 8-ball response. And we could say this is the right answer. In general, planes are using barometric pressure, an anemometer, to determine their altitude. And so that's calibrated to a standard, an international standard for the sea level pressure. So it should be really, really close to, say, a vertical datum defined around the sea level. But let's take a look at what these mean. Now, my skills are not that great when it comes to art. So please forgive this illustration, but if you'll accept an idea of ground level and sea level, and you can see my pretty waves here, and maybe a tree or vegetative line that's above ground level, there are many points we could try to reference our height from. We could use that mean sea level idea. Now, this seems at first glance a really good idea, but water is affected by gravity too, and not just the gravity of the planet Earth, but also the gravity of the moon. The moon is a very, very large mass and has an attractive pull proportional to that mass and the distance. So the tides, the actual level of the sea changes by time of day, time of year, and honestly, in position on the planet based on the density of the local ground, or planet, I should say. So instead of sea level, we could also maybe use that ellipsoid definition. But that ellipsoid may not be really close to the ground at any position. It could have some significant deviations, but it's a good reference too. Or we could use that notion of a geoid I mentioned before, that equipotential surface. So there's a number of different options we have, and actually height's often expressed in many of them. So if you had some point of interest and you have the distance from the ellipsoid, that's called the ellipsoid height. If you use the geoid, you can measure the geoid height. And then there's the orthometric height. Now, just as it's important to understand when you use latitude and longitude, what datum was that latitude and longitude defined in? That says, what's the reference system for that latitude and longitude? When you talk about height, you also need to be equally clear in what type of height you're talking about. And many of the calculations for computing distances or other things involving location, projections, which we'll cover shortly, need the right units of height. So now let's go back to coordinate systems. I've mentioned latitude and longitude a number of times, or longitude and latitude, which isn't the way we often say it, unless you really think about it as x and y again. There's other three-dimensional coordinate systems that are very frequently used. Geocentric is another way to describe what's often called as Earth center, Earth fixed. That would be a XYZ position, or Z if you're say that, where the origin is at the center of the planet. There's also local Cartesian systems. Commonly used are Earth, oh wow, that should be east north up, please forgive my typo, or northeast down. Earth north up, that's pretty close. And then there's a bunch of other ones like local spherical or projected. And we'll cover projected in a moment. Local spherical is actually azimuth, elevation, and range, another very common system. So before we actually start looking at how to move between these, let me ask you a quick question on distance. What's the shortest distance between 2 points on the surface of the Earth? Straight line, great circle, rhumb line, or a tunnel? I think a tunnel might actually be the best answer, but in general, the answer that's widely accepted is a great circle. That is a path that involves the circumference of the sphere. So let's take a look at some of these distances and what they look like. So those points I just made a few moments ago were done with the notion of say, a geopoint. A geopoint in MATLAB is a way to represent a latitude and a longitude. And because we need to be explicit, you can see I have an additional argument about what datum it was defined with respect to. Now, actually, this is just a label for my purposes. MATLAB isn't taking that datum into account. If we look at geopoint in the documentation, it takes a latitude and longitude. Those name values could be any things I wanted, and for our purposes a few moments ago, it was useful for me to identify those points. So when we were displaying that, I was using a web map. So we can create a web map, and we can define markers on this map. But going back into that prime meridian I said earlier about longitude, if we zoom in here into London, and where the Thames does its little dipsy-doodle here, there is Greenwich Park. And the prime meridian is what passes right through Greenwich. So if I wanted to make a web marker, I could make one, say, approximately, let's say 51.48 degrees latitude and 0 longitude. No deviation off of that. That should be pretty close to Greenwich Park. Now, I had a few other points defined. So we have this point, WGS point. That was my initial latitude and longitude on that University of Southampton. And I had a few other points defined. If we give ourselves a reference ellipsoid, the Earth, and we'll say meters again, we can now compute the distance between those points. The distance, get some help on this real quickly, takes a pair of a latitude and longitude and another latitude and longitude. If you do not give it any further information, it's going to use a sphere. And so if we're talking very, very large distances, that'll probably be okay. For very short distances, depending if you're on the equator or near the poles, those numbers could be off by several hundred meters. So to be clear and precise, we're passing in a reference ellipsoid again, using that WGS 84 ellipsoid. And when we calculate the distance between two of those points, it was 118 meters between the pair that were in the WGS datum and the OSGB datum. The WGS to ED, the European datum, was 73 or 74 meters. That's a significant distance, and that's not up at the poles. Now, these aren't the only coordinate systems in use, and we just covered that. Let me go back to the mapping toolbox and the documentation. Under coordinates and projections, you'll see there's a lot of coordinate systems, whether geographic or projected. And if we look at those 3D coordinate systems, there's many, many ways to convert from the different systems. And again, this is one of the key points is if you just throw a latitude and longitude into a conversion routine, you're implying something about the system it was defined in. So when we look at geodetic to Earth center, Earth fixed, the geocentric system, we not only need to know our latitude and longitude and h, which in this case is our ellipsoidal height. That's the height off that reference ellipsoid. We also need to know what that reference ellipsoid is. So the key takeaway I hope you're getting is precision. You need to be very precise about your position, and sometimes that just means carrying around an extra piece of information. So converting that latitude and longitude and saying exactly on the surface of that reference ellipsoid in meters, I get this position here, XYZ. That's how far it is in meters from the center of the planet. So I think we've spent a fair amount of time covering some of these ideas in coordinate systems and the different systems, and even how to convert them. It would be doing a great injustice if I didn't cover a little bit about projections. Now, the problem with the sphere is it doesn't flatten out very nicely. So the purpose of a projection is a way to represent the information on the surface of a sphere in a flat manner. So there's several different broad categories of projections. A cylindrical projection is if you wrapped a cylinder around the sphere and made it tangent along, say, in this case, I think it looks to be the equator, and then flattened that cylinder out. That would be a cylindrical projection. A conical projection also has a point of tangency that's another circle along the planet, but this one is now not necessarily at the equator. And so this cone can then be flattened out. And you can see it's doing interesting things to the South Pole here. Now, the azimuthal projection is kind of taking a cross-section, if you will. Now, there's many, many projections, and I'm not going to say anyone's perfect, because you're going to have distortions somewhere, whether it's in the shape, conformality, in distances, in directions, or in area. So you can choose a projection that has a lot of very good information for a small region or a large region, but something's going to have to go. So let's take a quick look at what that looks like. I'm going to start with a small region of latitude and longitude. And we're going to build a specific map axis. So once I make this axis, there's some things to take into account. When I say a map axis, in MATLAB, you can get an axis very easily. And it's going to be in terms of x and y. It's going to have no notion of the fact that geodetic information doesn't play nicely in x and y. So when I get that axis, it has things like an x limit and a y limit. Now, the USA map did something very, very special for me in MATLAB. It gives me, under the covers, a projection. Now, this projection was selected specifically for the region we're looking at. What you may recognize now, if you're familiar with the U.S. geography, is the Washington, D.C. area. We can add some labels to make this a little bit clearer. So we've got the District of Columbia, Chesapeake Bay, and Delaware. So where that projection information was stored, where that's actually hidden, is if you say GCA, that gets the current axes for the figure. There is also a notion of a map axis, GCM. And that map axis has a lot of information, the projection, the reference ellipsoid, which we're calling a geoid here, and the limits in terms of latitude and longitude. Now, you can make a different USA map. So I can pick one that's optimized for any particular state, or maybe the contiguous states. And if I do that, I'm going to get a very different axis. In this one, it was an equiconic projection. Now, if we wanted to add the states on here just to see what that looks like, it's a little bit more information. So the things that are helping here, GeoShow. It's a way to display data onto that map axis. The USA map, there's a similar functionality for the world map. If I want to make an axis that's appropriate for a specific part of the planet. Now, there are a lot of projections in MATLAB or supported in MATLAB. And if you go to the documentation for projections and parameters and we look at a summary, here are those different types of projections I was talking about: cylindrical, pseudo-cylindrical, conical, azimuthal. And you'll see there's a whole slew of them with different properties in terms of what they preserve and what might be distorted. And one of the things that I'm not going to cover in today's presentation is the math behind projecting into and out of these coordinate systems. But I will say that the projections are actually pretty straightforward. And if you're using a tool, hopefully it's going to have a lot of, like the mapping toolbox, ability to help you deal with projecting into and out of them. Sorry for the scrolling here. For projecting into and out of the coordinate systems for points or regions in terms of vector data. So, the key takeaways. There was nothing wrong with the GPS. There was nothing wrong with that map. What was wrong was with my usage of two numbers. A floating point value that was valid for latitude and longitude in a specific reference frame, the datum. When you're dealing with positions, it's important to understand what reference system you're using. That's not just the ellipsoid or the datum, which defines an ellipsoid or has a but also the height. And when you're dealing with projected data, knowing what that projection is and what it's based on so you can move data into and out of it. The mapping toolbox I used a little bit today to kind of look at some of these ideas, bringing in some data, accessing the web map and the different layers, and doing some of those calculations. Some very useful references include Van Sickle's Basic GIS Coordinates. I think it's a phenomenal reference in that it doesn't dig very deep into the math, but gives a very high-level understanding of the concepts.